hi friends of the sun. We're here now with Ezra and me, and we're going through the paper. And yeah, Ezra will discuss the paper.
We'll all discuss the paper, but perhaps I'll be something of a guide as we go through. So how do we want to do this? Do you want to hold the iPad and we'll just scroll and I can talk through here?
Yeah.
So the point to make for this paper is that neither Hannes or I are authors, and by extension, everybody here, unless the authors are in attendance, is equally an author and thus can contribute equally to this conversation. So as we talk, please feel free to turn your camera on, unmute, say this doesn't make sense, this does make sense, etc. You can drop comments in the comment section. I think we should be able to see them over here.
Yeah.
But yeah, other than that, as Hannes said, we intend for this to really just be a discussion rather than a presentation. So I think we can just start by we'll go section by section. I'll kind of talk through it, maybe summarize it, maybe steer people toward what I think is like the key intuition for this section, the big idea, and then we can dredge up things that don't make sense, and then see if we can resolve them as a group, and then go to the next thing.
I will start with the figure.
Well, let's start with the title of the paper.
Yeah. Okay. But finally, let's start.
All right, ready?
A general framework for inference-time scaling and steering of diffusion models is the paper from our friends of the sun, who we've also had here at some point. And yeah, I think this figure here explains rather nicely what's going on and what's going on, but not what we want to do. So Ezra, what do we want to do?
So the overarching point of this paper is to inference time steering in some kind of principled way. And the idea is that we're working as Hannes is highlighting with this kind of tilted potential. We've trained some model, this model P theta of x0, this is your diffusion model, your flow model, what have you. And inference time, we actually care about biasing it via this tilt toward this reward function. And the whole point is that I want to be able to inject signal about this reward function at inference time without kind of tuning or training my model in any way, hence inference time steering. And so basically this paper is presenting a way of doing that using techniques from like sequential Monte Carlo-esque stuff. So I think this picture basically gives the big idea of this thing, which is that we're basically going to be running many trajectories at once, and we're going to come up with a smart way of basically culling the trajectories that seem less promising in a principled way, and investing compute in precisely those trajectories which we think have the best chance of obtaining high reward under our reward function. And yeah, so that's exactly what's going on in the picture here. We have this prompt, a green stop sign in a red field, and presumably our reward model is the likelihood of this prompt as a function of our terminal sample x0. And right, so on the very left, you just have kind of the traditional paradigm of I'm going to sample, I hope I get something good, but maybe I won't get something good. And a slightly more refined attempt is to just do this n times in parallel, this best of n. It's very self-explanatory. You get n things, and then you can evaluate each of them with your reward function, and then you just pick the best one. Very straightforward. And on the right, we have basically what this paper is proposing, FK steering, where basically at intermediate points throughout my trajectory unrolling, I'm going to stop. I'm going to say, I'm going to have some notion of intermediate reward. I'm going to use that to kind of inform which trajectories I should stop, which I should keep going. And then I'm going to kind of duplicate the ones that I think are most promising and invest my compute in unrolling those guys. And I mean, for people in the audience that are familiar with sequential Monte Carlo, this is very much that. This is kind of how do we do that with the pre-trained diffusion model. Yeah, I think that's the big idea here.
Okay, and then I guess questions that come up now, what will this intermediate reward be, right? Because it's clear, or if you have a reward function, like for example, some model that takes in your let's say you have clip, and your clip takes in this prompt and then takes in the image that you generated, and then it gives you a score, how well these two fit together.
Yeah.
Like I guess image here maybe and this prompt, and how well do they fit together, then this can be your R of an x0. But how do we come up with these intermediate rewards is a question, and then also how do we like end up with this correct procedure such that we do what they promised us here. We actually potentials are selected just that resulting outputs are sampled from the tilted distribution, and this is actually the case.
Yeah, exactly. Okay. So we want to balance these two things. Let's scroll down. Okay, so exposition, background. Okay, results. Let's just know what we should expect. So basically, they take Stable Diffusion as the base model. On the right, they take like a DPO fine-tuned version of Stable Diffusion. And then they basically say, if you apply the paradigm we've described, or the technique we described earlier, we haven't actually gotten to what it is yet, with increasing amounts of particles, which is kind of how you scale this technique. You seem to do much better on these reward functions. Here they have gen eval, and I think it's just gen eval.
Yeah.
But it's, I don't know, this is, I found to be quite impressive.
So we have this score thingy here, and then here we have the base performance of this, I guess,
it's just the model.
Stable Diffusion V2.1 or
right.
V1 and blah blah or this thingy.
Yeah, exactly.
And then here we have if you just sample from this guy, then what is the gen eval score? Does anyone know what gen eval score is?
I did not know, so I looked it up.
That's good. I did not look it up.
So gen eval, okay, and I mean, if somebody in the audience, let me know if I'm confusing it with one of the other eval scores, but the idea is that for a lot of prompts, like generate an image of a banana to the right of a green tennis ball or something like that, it's like a segmentation scheme and then ranking scheme that will basically decide if like the actual like salient parts of your prompt are actually met. So it'll say like, okay, I see a green banana, or I see a banana and I see a green tennis ball, and they are to the right of each other, check.
Okay, and how is this automatically computed? Do you have a segmentation model or something like that, and then a classifier?
Yeah. So you'll kind of segment like the principal things, you'll classify them. I see banana, I already forget what the prompt I came up with was, a green tennis ball, and then you also have some module to say that one is to the right of the other thing, and then
okay.
So basically, if you can enumerate like the constituent parts of your prompt that can be like verified with this segmentation scheme, and then you extract the generated image and just confirm that these are right, that's basically what gen eval is doing, I think.
Why do we argue that this is better than having like a clip score, for example?
I think this is just a more specific, like a clip would just be more holistic. It's just like kind of a more. Seems more specific. Like this kind of is like like the steric flashes of like image generated. Like you actually want to make sure like very specific parts of your thing are. Well, maybe clip would also account for this. I'm not sure about that. It's just an alternative to clip, I guess, is one.
But it's definitely more heuristic, and we come up with these.
They're all heuristic, yeah.
Okay, well, but then so on the x-axis, what did you say these are?
So these are the number of particles in the scheme. So one of the parameters by which you can scale inference-time steering is by the amount of particles. So you can think of it as the number of chains that the number of trajectories that you're considering at once. It's kind of like the capacity to discover kind of high reward modes as you're denosing.
Yeah. Okie dokie.
So intuitively, it should get better as you go up.
And then they also have this neat comparison here with DPO. Okay. So what does that mean? This fine tuning of the model.
Well, I mean, they take the base, and instead of attempting to obtain higher reward samples by just using inference-time steering, they will actually fine tune the model itself.
So we fine tune the model itself to produce samples that adhere more to our reward that we.
Yeah, and I don't. So then what you could do is apply FK theory to your DPO fine tuned model. I don't think that that's what they're doing here. I think that they're just they just have it as a baseline.
Yeah. And it's this is nice to see how like DPO works.
Yeah.
Wait, so also what's the difference between DPO and diffusion DPO? I mean, aren't we dealing with a continuous space diffusion model in all of these cases? So why can we do standard DPO? Or have you looked into this?
I have not. I have not had a chance to look into this, but
if anyone in the chat knows.
Oh yeah, this is a chat moment. Are there any DPO versus DDPO experts in the chat here? I'm sure somebody.
Also, I thought the DPO came out before the DDPO. Anyway.
Wait, if you click on Wallace et al., maybe this is not the actual DPO paper. This is DPO for diffusion paper.
Okay, that didn't give us Wallace et al.
Yeah, Bram Wallace. No, Bram Wallace right there.
Diffusion model.
Yeah, okay, it's this paper. So it says it's like a separate thing.
Okay, so this is also a diffusion model thing.
So I've downloaded this paper, but I have not read it, so I don't want to comment.
Okay, let's go back up to our friends.
Right.
Okay, then I think everything is right. Now here we're just looking at our FK steering. How much can we get? And of course we would want to know how much better, and especially in terms of compute, how much better is that compared to our just simple best of n sampling.
Right.
And we'll also have some numbers on it later, I guess.
Yeah. So yeah, they have, I think, some pretty exhaustive experimentation in the results section. I don't think there's anything here that shows best of n.
Yeah.
But yeah, I mean, these things scale very well. It seems like you can just kind of scale a base stable diffusion model to be competitive with this much larger model by just FK steering stuff. Okay, so what do? They propose this Feynman-Cat diffusion steering, and then they show that they also basically show that previous schemes that do SMC-like stuff with diffusion models. I think the primary example being this twisted diffusion sampler. There are special cases of their thing, and then they show that it works pretty well.
Yeah, but then let's maybe try to. Okay, whenever we have a figure, I guess we kind of have to address it a little bit.
Yeah, this figure is very just, this is like an aesthetic sanity check, I guess. You can see that it seems to be doing better as opposed to just like vanilla conditioning.
Does it? I mean, in this one, yes, right? We actually get a birdie and...
Yeah, there's no birdie before. I think that's important.
And this one, yeah, good. Now the sandwich is actually a bit purple.
Yeah, brown. The knife is brown. There's no clock in the last one, in the original one, and now there's a clock. The dog, a photo of a green tennis racket and a black dog. Okay, it's also seems to be better.
Yeah. Anyway.
So yeah. Anyways, okay. It looks like it's making an improvement.
But then let's actually talk a little bit about this related work and the stuff that they're comparing with here, because I mean this stuff maybe not so. Yeah. Okay. They talk about fine tuning some existing models, and we also had this guy here once in the reading group talking about some of his work, but that was not actually about fine-tuning, right? That was just inference-time steering.
No, that was adjoint matching. This is adjoint matching.
Yeah, adjoint matching, where we fine-tune toward the... and is this also what they cite here, adjoint matching? This guy?
Yeah, that's quite... Yeah, it is fine-tuning.
But then we have also this inference-time steering, where in the beginning they talk about the standard. If we just take the gradient of some reward function or a noisy reward function and then combine this gradient with our score, then we can, on principle, also sample from this tilted distribution. But the issue is that our intermediate reward functions often are bad, and this doesn't turn out to work all too well. And then here, this twisted diffusion samplers.
Yeah, so
maybe we should talk about that more.
Yeah, so I think it kind of makes sense to just talk about what FK steering is, and then talk about TDS as a special case of this, rather than to bring up all the machinery of TDS and then discuss FK steering after that.
Yeah.
Because I think one of the contributions of FK steering is they kind of lay out like a unified design space for the construction of these like SMC-like samplers, of which if you plug in a special case, the claim is that you get TDS.
Good. Then
So I think we should move on to.
I'm happy to maybe get some notation down.
Right. Okay. So yeah, keep going.
Yeah, we always have this in the diffusion models that we consider. We now basically always have some conditioning. And do they write something about the reward here somewhere?
There's no reward here. We haven't introduced reward. This is the base model with no reward.
Yeah. Okay. Yeah. Okay. Now let's. That was a German word. Let's also mention that we're talking about paths here, and that we always start with our big T, and then so the big T is something very noisy, and so something from our prior, and the 0 is our something in our data distribution. What else? What else? Nothing else basically. And now we introduce this reward here. So we're just given by God that we want to sample or that we like samples that have high scores under this reward. And then what we want to sample from is this guy in the end.
This regularized
and
distribution.
There's also kind of a like unclarity in specifying what we actually want to do now, because there's this lambda, and yeah, I mean you can change this lambda and then you essentially want to just sample this, or you can change it such that you're essentially just sampling the Boltzmann distribution of this guy. Wait, is that correct?
Well, it depends on what lambda. It depends on how strong you're.
But yeah, can we make, if we make lambda extremely large,
then I think you just get like a temperature 0 reward. Then it's like. But it is lambda. I think is the regularization, like inverse regularization strength or something. If lambda is very large, then intuitively it seems like your model itself doesn't matter very much, and you just.
Yeah. Okay. So it is correct what I said. But then, okay, let's also talk about the fact that now here we have this I, which talks about the or which indexes the particles, the multiple particles that we'll be generating. And then I think we're pretty happy to. Okay, let's look at this thing here once more. So we have the lambda guy, which tells us basically the strength with which we adhere to our reward. Then we have our I, which indexes our sample. We have our condition, and I guess our reward now also depends on the condition. Good. Then Feynman-Catch steering.
Right. So right. So okay, the idea is that essentially we want to. So the thing we're targeting is I want to generate samples. I want to generate these trajectories so that x0, when passed through this reward function, has high reward, right? And the point is that I want some way of I mean, if we recall back our picture from the beginning, where we want our scheme to operate at intermediate points along the denoising trajectory. So I want to have some notion of what my reward is at intermediate points, and then the big idea is I want to have a way of, at intermediate points, kind of saying which of my samples are the most important. And so this paper does that via the introduction of these objects called potentials, which bias. So these objects here are paths, these denoising trajectories, and basically what they're going to do is add on these intermediate potentials, which in aggregate over the whole trajectory kind of corresponds to the desired reweighting of just reward function of x0.
Can you talk about the from paths to, okay, so we want in the end something, and this is not what we said at the beginning that we want. And here we're now talking about paths that we want to be, and this distribution over paths being tilted by the terminal reward. And why is that? Why is it the same?
Well, the idea is just that it's the same because the thing we're tilting by is only a function of this terminal point, and so like this tilt action effectively what you're getting is you're just tilting the you can think of it as like you're tilting the x0 marginal and then just implicitly this results in a tilt of the resulting path measure. And you can think about just thinking about this directly in path space by just, I have a trajectory and kind of the weight I'm going to apply to the trajectory corresponds to the reward of the final point.
Okay. Yeah.
And so so in the same way that like in annealed importance sampling, for example, your importance sampling, over trajectories, which, gives you equivalently you're doing this in an unbiased way over the terminal sample, just because the terminal marginal, the distribution over x0 of this trajectory is just the thing you care about.
Okay.
That's essentially the reasoning.
Then shall we look at what's going on here?
Right. Yeah. So what's going on here is they're defining this new distribution over trajectories, which is a tilted distribution, and this is the notation here is it's this FK. They call it the tilted thing is PFK, and it's just another distribution over denoising trajectories, and it's obtained by taking the original thing and then tilting it by this product. And this product,
first of all, this thing here corresponds to like a partial trajectory.
Right. So this is a partial trajectory from 0 up until time t. Right.
Depending on whatever our t is.
Exactly. Yep. And we're going to this is obtained from our normal denoising trajectory. So p theta of xt, the first term on the right, is just our normal model trajectory for this up to this little t. Now what we're going to do is we're going to tilt this by something. The thing we're going to tilt it by is the product of all of these potentials. And the reason it makes sense to think about the product of all these potentials is you can think about our model trajectory, p theta of xt, xt minus 1 all the way to xt as p theta of xt times the product of a bunch of transitions. And I can think of each transition gets its own biasing potential. And in aggregate, this gives me a product of biasing potentials.
Each transition gets its own biasing potential here.
Yeah, so this is how we jump to the next one. Basically, we make a transition according to the model, p theta of xt given xt plus 1 and c. And then additionally, we inject this biasing potential. So we're basically, in the same sense that our original model can be factored as the product of a bunch of transition kernels, our tilted model can be factored as the product of a bunch of tilted transition kernels, each of which is written as the model transition kernel multiplied by this potential g of t.
So we'll start out with this guy, I guess.
Yes.
And they say this guy for them. Oh yeah, here they write it down.
Mm-hmm. Okay, and then I'm going to take another, and then I'm going to take another transition step according to my tilted kernel. Or I wouldn't say a transition step, but this is how you would construct kind of your target distribution. This is not the thing I'm sampling from, but this is the thing I would like to sample from. So that's kind of the core idea here is that instead of having a single tilt at the very end, I'm just going to factor this tilt across all my transitions. This is not completely novel. This is kind of something that people have done before, where you factor this tilt. I think in the TDS paper, this thing comes up, but this is kind of framed in a more general way. And also notice that we're framing this in front of a potential G that's kind of decoupled from a reward, right? So we haven't actually talked about how the reward fits into this thing yet, right? Which is important. And so now we have to ask ourselves, like, what are admissible G's? Like, okay, I'm tilting by a bunch of G's, and how do I know that they actually correspond to the thing I want to tilt by? And the answer is that the thing I want to tilt by in the end is just this function of the terminal point. It's just the exponential of my reward strength times my reward, right? And so what this means is that the accumulated effect of all of these intermediate biasing potentials should yield the final terminal biasing potential, right?
So that's what you're saying here.
Exactly, right. So if I can construct a bunch of G's which satisfy this property, then I've obtained a sort of sequence of tilted transition kernels so that sampling iteratively from these tilted transition kernels will yield the full tilted distribution over trajectories that I actually care about. So now the problem becomes both how do I construct these potentials by which to tilt my kernels, as well as how do I actually go about sampling. So those are the two things those are kind of the two big ideas that we need to unravel.
So I guess let's start with sampling,
right,
and just assume we have them, because that's the next thing in the paper.
Exactly. Okay. Right. So sampling kind of let's so the idea with sampling is to kind of pull from the SMC literature and just say that kind of at every point kind of I have some target density. In this case, it's unnormalized because I just have this potential, and I have some proposal distribution. And what I can do is I can let's see order.
So maybe so what's going on? We have our let's say t and 0, and then what you're talking about now with at every point is we're here at a point along our denoising trajectory, and then this sort of is our next point.
Right.
And do they call this S and T here? No, they call it just T and T plus.
S and T, I don't see any S.
Yeah, previously they had this S and T up here, right? But now they just call it T plus 1. So we have our T and our T plus 1. And these are now the steps that you're talking about, and we want to sample from this tilted thing to this tilted thing. All right, we have a sample that's living here right now, and then we want to transition it to a sample, and then these are our distributions.
Right.
This is our tilted distribution, and this is another tilted distribution.
Right. So let's just examine one jump. Let's just walk through how one step would work.
Yeah.
Right, in pictures. So let's draw in our diagram. Let's draw like maybe 4 little particle trajectories.
Oh shit! In this diagram, you want 4 trajectories.
Yeah, let's go on the right. Well, because I want to show, because that's why it's an interacting particle system. Not as, otherwise it would just be a single particle interacting with itself.
Okay, but 4 trajectories will require some drawing skills.
Oh, you can just redraw on the right. Okay. So we have 4 things, and the assumption we're going to make, this is kind of like a kind of asymptotic inductive assumption. Let's just assume that these particles are distributed according to PFK, right? And we're going to describe this update scheme by which the next set of particles will be distributed according to PFK sub t. Right, so the purple guys are distributed according to PFK t plus 1. And we want the guys on the next iteration to be distributed according to PFK of t. And the problem is that we don't have access to the transition kernel for PFK. And so what we're going to do is we're going to take each of these particles, we're going to evolve them under the kernel of the model that we do have access to. So that's our model. So we're going to for each guy, we're going to sample using our model. So that's p theta. So we're going to sample from this p theta of xt given xt plus 1, conditioned on c too. Yeah, exactly. And then we're going to get a bunch of particles, and we're going to say,
Oh, wait a with this guy.
Yep.
This guy, this guy, and this guy, and maybe our transition was like this.
Oh, so maybe we can in green draw XT sampled from this.
Yeah, my color scheme here isn't.
Whatever. Okay.
Yeah, and then.
Okay, so now we've sampled these green particles from this transition kernel, and we need to, basically what we're going to do is we're going to assign weights to them. We're going to assign these importance weights to them. And these importance weights are basically dictated by they are essentially the importance weights of the FK, the unnormalized Feynman-Cach transition kernel over the transition kernel that we use. So this is what this display is giving us.
You now want this
GT of I. So if you let's scroll to the right a little bit on the big screen, so that everybody else can see what we're working with here.
Oh, what do you mean? Like, yeah, we want to now assign to each one of our eyes.
Yep, exactly. And this basically is correcting. This is basically I'm reweighting for the I'm reweighting from the transition kernel I did take to the transition kernel I should have taken.
A proposal generator tau. So you're saying this guy here is our model, for example.
So yeah, so tau is usually right. So the true transition kernel is given by take a step by our model and reweight by GT of GT. But what we're doing is we're actually just taking a step from our proposal tau, except seemingly everywhere that this is used, they take tau to just be the transition kernel p theta, and so the p thetas cancel, and the importance weights are just the GTIs.
Okay, so.
But in generality, I guess it doesn't have to be that way. And you could imagine, for example, taking sometimes people talk about gradient guidance, where you kind of inject the gradient of your reward into your thing, and you use that to inform your step. But if we ignore that, then this collapses to just G of T.
This thing is what this becomes.
Yes, exactly. So now we say, okay, we've attached an importance weight, and what we're going to do is, instead of considering 4 weighted particles, maybe it happens to be that one of them has a really low weight, so it's like really unimportant, right? And the idea is, let's assume for now that G was chosen well, right? G was chosen well, so if it has a low importance weight, it's not a very promising sample, and we really don't want to have to do a full unroll for this thing, right? Rather reallocate our future compute for these more promising samples. So the next thing we do is so after computing these importance weights, I'm going to resample. We're going to resample these points. And basically what we're going to do is we're just going to essentially, if I have 4 points, I'm going to sample 4 new points from my existing set of points, where the probability that, or the likelihood that a given point is any of these 4 is just proportional to its importance weight. So this is just a SMC resampling step. And you can show that kind of this, in the limit of infinite number of points, this kind of gives you an unbiased way this is an unbiased change of the points that you resampling step.
So let's say our reward for this point, where to draw. So for this point it was 10. For this point it was 90. And for this point it was 50. And for this point it was 1. And then maybe we end up sampling this guy here once, because it has weight 50, and this guy here 3 times.
Yeah, that seems, that's possible. Right, and so I've resampled, and then the idea is then I repeat it. I repeat this step a bunch of times.
So these guys are now the XTI at T. The XTI.
Yeah, these are the XT. Yes, this might be slightly. There might be some off by one thing. If you look at they start by resampling, so it might be modulo exactly the ordering that they do it in. Those are the indices. But yeah, so if we look at this algorithm for their Feynman-Cach diffusion steering, this is exactly what they're doing. they start each, so initially they start all the points by having this initial weight, which is just gt of xti given c. And they're going to, they start by resampling in the way we discussed. And then
okay, so we weight all of our samples with the GIT, and then we sample the AIT, which then are just identical to XIT for the XIT that we sample.
Right. And then we're going to take those resampled ones, we're going to then just generate the next generation. So set us up for the next step. So we propose using our transition kernel.
So
we
the
reweight
model step. Then we compute the weights again. Right. Using.
Yes, for the next step, using the thing we discussed.
Yeah, using the things
yeah, so there's probably in many cases that those cancel. Yeah.
And then we do this one again. Pretty simple.
Okay, but of course, we've just been using these black box G's, which we haven't actually related to our reward. And so the next step is to say, okay, how do I get good G's? How do I get a good reward? And actually, it's kind of interesting that they even decouple G from the reward. I think that's also kind of an insight, maybe, unless another paper is on this side.
I like this.
No. But okay, so how do we get our G's from our reward? And the idea is they have several schemes. Yeah.
So if you say, unless another paper had that inside, I think that's what like the FK steering literature does. And here now it's applied to diffusion models. So
okay, yeah,
I think it might be that essentially the only thing that's going on here is that yeah, we are doing FK steering, but well, we have this proposal.
Yeah. Okay. So it's FKIPS, I think, is the stuff in the literature.
Okay.
Right.
Then why do these, or first, what are these G's and why do they fit our requirement? That's
right. Yeah. So they have these 3 different ways of getting G, and basically, if we recall from earlier, the only thing they have to satisfy is that they have to multiply out the desired reward. And so one way to do this is to just get them to telescope so that consecutive terms kind of cancel each other out. And that's this difference thing right here. And the claim is that this is similar to Wu et al. This is the TDS paper, which we can discuss after we kind of get through this section. But the idea is here is the intermediate reward is kind of how much better you are doing now than the previous step. And intuitively, it's not clear that this is exactly what you want, even if it gives you even if it gives you something very, technically it satisfies the condition for G in the sense that you're paying attention to kind of the difference rather than kind of some more absolute quantity. And so I guess they try and rectify this with this maximum reward. And the maximum reward is you just kind of do whatever intermediate things. And in this case, you take the maximum reward so far so that you avoid this phenomenon that we were just talking about for difference. And then you just divide out by everything that you saw before times 0 so that you satisfy the thing. So this is kind of like artificial dividing out. And then I guess one way to...
Wait a second. Where's the dividing going on?
So you see G0 is the thing we care about, and then you divide out by everything else. So the product is trivially is equal to the thing we care about. And you can reason that this is it's not actually that bad to divide out because you've, yeah.
So it's basically like we might now end up with some trajectories where we have our little path here, and then let's say I'm drawing the mean now, the mean of the path. Let's say it's like a continuous. I'm drawing a continuous unimodal path, and I'm drawing the mode of it. And then it might be that we have a situation where then we have, at the very end, a discontinuity where, it's there is then the actual mode. because we do this last.
Yeah. So right. So it's, if this works, maybe there's something to be said about it relying on like some like finite particle proxy. Like if you only have two particles, for example, and by the time you get to the end, both particles are probably pretty good. So this probably doesn't really have much of an effect, right? Because you're just resampling from two things that are like already reasonably good. But if you have an infinite number of particles, then maybe you have some like tail events that gets like really, really upweighted, and you sample something that's like maybe less desirable. I don't know. Like intuitively, it seems like maybe this could happen. If you're only using like within 10 particles, or 2, 4, 8, 16, any of the quantities that they test, then probably the things you end up with once you get to this terminal step are all relatively. I don't know. Intuitively, it's
like either you don't need to do this anyways, or it's like very inefficient to do it. Right? If you, in the cases where you still need to do this and have this final step where you then reweight things correctly, well, then your two distributions here at almost the end and at the end, there they don't match up. And if they do match up, then you don't really need to do this reweighting where you cancel out all the previous weights that you had.
Yeah.
That's just a thing for writing it down for the sake of it actually being asymptotically correct. But in practice, it shouldn't really matter, right?
In practice, it shouldn't really matter. As in, it seems like the kind of thing.
And you're then just doing important sampling from like a potentially from a good distribution to a good distribution, and it doesn't really matter, it's almost the same already. Or you're doing important sampling from something bad to something good, this one singular step, and then if they're not almost the same already, then this will be super inefficient anyways.
Sure.
Yeah, okay.
I'm not sure I completely follow, but
it's clear that we need need this thing here for it to be correct. And
although it seems like it would give you strange results if you had a really unlikely thing that stuck around. But it just, in practice, I think to your point, you don't get those things because when you sample with small numbers of particles, they're just all pretty high weight because you've already filtered out.
Yeah, okay, but then the sum one, we use the same trick. We just don't construct something that follows our condition, and then just at the end resample everything to actually follow our condition.
Yeah, exactly.
But can you give some intuition on like why would I want always to choose the most improving thing? Why would I want to always choose the highest reward that I've observed along the whole trajectory? And why would I want to consider the sum of all rewards along the trajectory?
Okay, so I mean, for the difference, I think that
it's the most different.
I say the intuition is that you don't have to do this division. It's kind of one of the most natural constructions if you just want to satisfy this constraint.
Yeah, but it feels like you would end up not with such good samples.
So intuitively, it seems like you would not want to do this. It seems like the reason to do it is just because it technically works it fills it checks the constraint that G has to match rather than that it makes sense intuitively because it seems like you want relative improvement doesn't seem like what you want to care about. And again, my intuition is not I'm not going to claim to understand this extremely well on an intuitive level, but it just seems kind of from a first pass like maybe that's not exactly what you want.
I mean, like let's consider so in this drawing here now, let's remove. In this drawing, the x-axis now corresponds to reward, and the y-axis corresponds to time. So here's t, and here it's 0, here it's t, and here we have the reward. We want it to be high. And then we have a bunch of particles doing their movings.
Yeah.
Let's say we're here, and then like this is a possible trajectory, and then we have this guy. And then at this point here, like from here to here, in this scheme, we would give this guy, the guy down here, a higher likelihood than the guy up here, which just seems wrong. But of course, this trajectory that we're getting, that's not the, like this trajectory is, no, I mean the relative improvements here are the same. But yeah, I guess we get the point that I'm trying to make, maybe?
Yeah, which is just that it doesn't seem like what you...
This seems the most natural to me, like to choose the sum and then look at the total accumulated reward so far.
Yeah, no, I agree. And I think we'll see that, I believe, like, I mean, at the end, I think they see that max performs well, but similar to sum, and I think they both perform better than difference. But yeah, this intuition makes sense.
Okay, I guess then here they also quickly state that they don't actually do this resampling at every denoising step, like, yeah, not at every denoising step, but only at some intervals of steps. Is that what they're saying here? Yeah, I think so. Then choosing intermediate rewards, right? So the reward is different from the G. G is the potential, and now the reward is used to compute the potential.
Right. Yes, this was a nice decoupling thing that we thought about. And then I guess the other comment is that your weights actually become a little more complicated if you don't do it every interval. But you can imagine you just take the
product,
a path importance weight on that sub-interval or something. Anyway, so choosing the intermediate rewards, yes, they discuss 3 different ways of constructing G from your reward. And I think kind of the big idea here is you use your model to predict x0 from xt, and you evaluate your reward, and then you just say that is your reward function here. That's your intermediate reward.
I mean, that's what you just explained is expected.
It's the reward of the expected, not the expected reward.
Yeah, sure, but the way you said it sounded to me like this is now all there is to it, but this is just one of the...
That's just one, that's one of the, yeah. And I misspoke earlier too. This is how they construct the intermediate rewards from the reward, not how they construct G from the rewards.
Okay, so I give you xt, and then you give me a reward by getting the expected x0 given that xt, and so they call it het xt, and then you plug it into your reward function and you pretend that this was an x0, and then this is our intermediate reward.
Right, exactly. And then the next 2 things kind of try and converge on instead computing the expected reward at x0 as opposed to the reward of the expected x0. And so the first thing that they do is to just construct like a Monte Carlo estimate of this by unrolling. I guess they just do like some number of unrolls, which seems very expensive.
Yeah, so this sounds super expensive.
And then they just take the average, and that will give you an estimate, a really expensive estimate. And then the alternative way of doing that is you try and amortize this cost by just learning this, and you just try and regress against the reward at the end, so that your optimal reward thing is just your expected reward. And at this point, maybe it's not inference-time steering anymore. Maybe this is just you're back at fine-tuning. You're not fine-tuning, but you're training something, which I guess maybe it's just whether or not this fits within
like
the framework.
Having to learn a noisy reward function. If
yeah,
we
exactly.
want to do our gradient-based classifier guidance.
So then I guess the question is, if you're going to invest this amount of compute, is it fine-tuning versus investing in a learned thing? It'd be interesting to see what the trade-off is. but yeah, this is just the direct attempt to learn the expected reward.
Okay.
Yeah. And so with that, I think we're now at the see how well things work. And yes, they have several experiments. They have they do stuff with images, with several different image reward functions. And then they do some stuff with text diffusion models and look at the perplexity. And then they have they look at different potentials. They just kind of they kind of look at the different dimensions of their design space and see what works. So I think we can just kind of walk through it and just see, okay.
Text to image.
Text to image models. Okay, they have this. Right. Okay.
Where do we want to look at? Do we want to read the setup?
Let's just look at the picture and then we can update.
Then we find what we need.
Exactly. Yeah. Okay, sounds good.
Okay, what's going on here? We have Gen Eva score again, image reward score. Do you also know what image reward is?
Image reward is some other. I looked this up at some point. I think it's some other learned reward function that supposedly encodes like preference information.
Okay.
But let's black box it for now. It's some other reasonable measure of image quality. And then Gen eval is what we were discussing before.
Then we have always the base model here, I guess. That's what's going on. Okay, let's take green. No, come on.
So, right, okay, so they just measure scaling these things with increasing numbers of particles. And they see that, I mean, this is kind of the picture we saw before. You see this kind of uniform improvement, although there's this weird stagnation from 1 to 2. And actually one of them gets worse, which is interesting. Maybe this is kind of some like small sample size. The reweighting isn't really very accurate or something. It's not clear exactly why this is occurring. But yeah, we see a similar scaling curve to the previous diagram. I think this is maybe like essentially the same information as the one that was earlier in the paper.
Yeah, that's kind of interesting. Like,
yeah,
what's the difference in Gen eval versus image reward that causes this behavior here, where the reward really doesn't improve, or Gen eval score doesn't improve, but it's like qualitatively what is happening in the change of the images that makes this image reward score improve while keeping the Gen eval the same.
You could say that maybe Gen eval is like more discontinuous or something, because it's not like some holistic kind of like image fidelity thing that I think image reward's like preference train thing, whereas Gen eval is like the cup is to the right of the other cup. So it could be that like, maybe you need at least 3 samples to get to hit upon a sample that would actually unroll to the cup actually be to the right of the cup. And if you don't have enough, then
anyway, I guess this plot here does not say anything new. This is
the same picture, effectively, right? Scale. I think this is just scaling the number of particles, and then they do a similar thing with these text diffusion models. Oh, they compare to best event here. That's new.
Yeah. Okay, let's get into that.
Right. So for each of these models, this is image. These are images too. They compare. They just compare sampling from the stable diffusion model to. Really, the interesting comparison here is between best event and these FK steering. They show that kind of uniformly it beats, although it's quite close to best event. And then actually in the second row, the one they highlight is actually not the best. Is one of the best event is actually beats it on the human preference score.
Wait, you mean in here?
Yeah, 265 is higher.
Oh no.
It's okay though. But on everything else, it seems to be higher.
Oh darn. Human preference score. That's not human based, right? Or like.
I assume there's a human in the loop somewhere.
No, they don't actually have humans in here. Right?
No, I don't think so. But yeah, so both best event and Feynman CAP steering seem to just like both do far better than the base model. But in a lot of cases, it's not clear to me like how much it exceeds best of n.
I feel like this,
At least on
right? If you always only look at your mean performance, then you would miss what you like the advantage that you get out of best of n sampling. And I feel like the image people, when exploring their architectures and so on, they never looked at like a best of n evaluations. So our models aren't really built for having high diversity. And if you have low diversity, then your mean might be the same as a model with high diversity. But the best of n and the thing that has high diversity, that could be much better than the thing that has low diversity. So,
right.
and then these models that have very low diversity, and they have less of a chance to leverage now these techniques like the inference-time steering with like the FK steering or best of n sampling. Yeah.
So you want to kind of turn the temperature up a little bit and then use one of these techniques somehow.
Yeah, for example, or you want to use the architecture that has a, I don't know, the architecture that for some reason is naturally producing more diverse samples under the same conditioning.
Yeah, that makes sense.
But maybe the diversity of these image diffusion models is already very high, and this is not a concern. Anyway, then let's get to the next table.
Next table is
fine-tuned models. Now they put it on top of DPO. What happens if we do best of n with the DPO?
I guess it's not there. Right. Okay. So next thing is this is text diffusion models. They measure perplexity, and then actually I'm not sure. Do you know what this dist 1, 2, 3 this diversity metric is?
Nope.
It's diversity of one different n-grams, I guess. Or I'm not very familiar with these language model metrics. Does anybody in the chat, any chat participants, know about what this dist 1, 2, 3 metric is?
No.
Maybe
it says in the paper it's distinct 1, 2, 3 n-grams.
Aha. Okay. Oops.
So we just check if it's unique or distinct. Where is it?
I think it was above the table.
Above the table.
Above the table.
Yep. Right here.
Oh wait.
Cola acceptability and distinct.
Distinct uni, bi, and trigrams. Okay, so it's like a measure of diversity, I guess.
Not sure what. Yeah. Okay. Well, distinct unigrams. Does it mean like how many distinct letters we have, or
tokens or something? I guess it's some measure of diversity. If it's higher, it's more diverse.
Okay, let's accept that for now, but only for now. So then again, we have our comparison of best of n versus FK steering. Yeah, and the FK steering is indeed better. But let's look at the diversity. How does that? It's essentially identical. MDLM. This SSDLM is much better than this MDLM. Do you know how SSDLM works? To me, it sounds like it's using some embeddings of words and then just running continuous diffusion on those embeddings. So
I think that's right.
Latent diffusion.
And noise word logics. Yeah.
Good.
So I think,
But then let's look at G. All right. In the previous section, we used two different choices of potentials, max and difference.
Okay, yeah. This is the table that I think we're wanting to see. So they actually compare these three different things, and so actually, yes, it seems like actually some I misspoke earlier. Some Michael needs to go. Thanks, Michael. Thanks for coming. Right. Okay. So yeah. So it seems like the max one is doing the best here, and this difference one actually doesn't do very bad, and they all do. What are these numbers? Different potentials on that. This is Gen eval. The average Gen eval prom score, which if we go back here, Gen eval. Wait, hold on. Why is Gen eval on this table between? It's like on the order of 0.5, but it's like. Oh no. Okay, never mind. Okay, that. I see. Right. Okay. So. None of them looks suspiciously worse than the others. I'm not sure if what that says. Does that say that maybe you just need to evaluate, like, kind of whatever intuition you might have, it only emerges at like larger particle, when using more particles or something like that, or there's some other limiting reactant that prevents, one of them from being obviously better, performing particularly better. It's not clear, but none of them is impressively better, I guess.
Toxicity results. Okay, now they just have a different reward function, and they want to make text as toxic as possible, which I appreciate. And right now they also, here we have a comparison between using the many reward functions and learned reward functions. Did we ever talk about this many reward function thing?
No, we have not.
Where is that?
This is the first time. Many is the one where they just sample a bunch and then take the average.
Right.
Okay, so gradient free.
Oh, right, yeah. Okay, so this one sounds much more expensive. Or these two are much more expensive. And we kind of would expect them to be the gold standard, no?
Why does one model get the learned and one gets the many? I want to see both with one.
Yeah. Why now we're not able to compare the learned with the many? That's that.
Okay, but we can compare them to the just normal FK. Okay, I mean, it seems like it does much better, but that definitely would make sense.
Yeah.
It does. It seems like, I mean, at generating toxic text, it seems like it does a lot better.
Well, then not much more to say here, I think.
But also you can just do better by doing more particles, it seems like. K equals 4 with learned, or you can just double the number of particles and you almost double the performance. I'm not sure if that says as well. Oh, and it actually does much better than best of n here. I wonder why that's the case.
Yeah, but then it almost sounds like to me not worth learning this thing.
Yeah, I would agree.
You just rather double the number of particles.
Right.
In that scenario, right? But if we, yeah, whatever. Studying different choices of rewards. Correlation.
I think that's the chart we're just looking at. Was the table was just higher, I think.
I see.
Yeah.
FK steering TDS. Oh, okay. Now they compare against some baselines. What time do we?
I have to run a little bit.
Yeah. But then I would say let's look at the appendix now and try to find if they have some comparisons between learned and many. I can never.
Oh, I mean, there are a bunch of tables.
Yeah, in these tables we only have different lambdas and so on. Nothing interesting. Good. Then let's maybe finish off with the question of what is now TDS in our FK steering framework.
Right. So TDS, my understanding of TDS is that they have a very particular choice. So there's no differentiation between these biasing potentials and the rewards. I think they basically choose G to be, I guess, so, right. So the claim here is that they're choosing it to be this, this difference reward. And then the reward is chosen so as to be of the form that we saw earlier, where you predict x0 and then you measure the reward at x0. And I think for the section of TDS that I read, the reward function was like likelihood of the conditioning variable given your x0.
Okay, so TDS, this paper basically does TDS, but then has additional options for the reward and for the potential.
That's my rough understanding, yeah, is that they basically identify TDS within this design space, and they say you can do all these other things, and we do these other things, and that's a special case of this thing that we lay out.
Good. Any other points? Or should we call it a day?
I don't think so. I think let's call it a day. Unless anybody else from the audience has any further points in discussion.
I think not. There's nothing happening here. So.
Sorry, can I have a question?
Yes.
Yeah, go for it.
Perfect.
Oh, okay, thank you. I thought there was a question period, but sorry, I just directed to ask you about the process of the FK diffusion, because I have tried on your code on some diffusion models, and I found that there might be something I think is a little strange with this FK process, especially for the resampling schedule. So this method is very sensitive to the lambda, right? I think you have already shown that in an experiment.
Okay, so first of all, we have not shown anything. We're not associated with that paper. Yeah, so you're saying the thing is very sensitive to the lambda, and I guess you can see that in these tables down here. Which table shows it best? Maybe this one. So here we have different lambdas, and then the Gen-Eva score changes a good bit, and lambda 10 is the best. Then here again, lambda 10 is the best for all these stable diffusion models.
Yes, I have used the recommended parameters like lambda in the diffusion process, and I have tested on several images to see the specific process of what kind of images are generated and resampled during the process. And I found that sometimes the sampling process will totally won't work because every scores are almost similar to each other. So there will be no resample process. So the whole process is almost the same as the best of n. So which means that in some kind of condition, the image will not be resampled. It's just the same consequence with the best of n. And sometimes the resample.
Sorry, what reward are you using for that?
The recommended, the max one.
Yes, but what is the x0 score?
X0 score. I just used the okay.
What is the reward that you just your target that you want?
Oh, image reward. Image reward. Yeah,
okay.
And it will be rescaled in 0 to 1, which was recommended in the provided code. Yeah.
And you're saying you can't get this to really work because in some cases the rewards for all samples will just be the same, and then it essentially ends up being the same as best of n sampling.
Do they ever report the effective sample size with their like intermediate things in this paper?
Yeah, and in some kind of condition, it worked very fast, and the samples are converged into 1 or 2 samples. Yeah, that is also very common during the process. So I found these two kind of, I think is a little strange, especially for the best of n part. I found that it is because the lambda choices. So sometimes the lambda is a little higher or lower for the method, and then it will converge to a best of n or converge to a very greedy selection.
Okay, so you're saying either the diversity of what you generate is extremely low, or the... Wait a second. Here we're also always still reporting then the performance of the, right, we're generating 4 particles, and then we're reporting the performance of the, okay. So you're saying that either essentially all of your samples are the same as the best of n, and they're quite diverse, or the samples are all the same, and there's just no diversity left at the end.
Yeah, and I increased the sample from 4 to maybe 8 and 16, and every time the outcome will be influenced by the lambda in a large scale, so it is very hard for me to choose the best parameter for the method.
Oh, so you're saying the optimal lambda also depends on the k. Why is this? Am I missing something here? Why would the k influence the lambda, the optimal lambda?
I'm not sure about this, but from my experiments, the influence is very huge for the lambda's choices.
I mean, all of these claims are only true in potentially very high numbers of particles. And so when you're only reasoning about 2 or 4, 8 particles, I think it's there could be very strange phenomena that show up.
Yeah.
Especially that are exacerbated by your potential changing wildly by lambda. And it's hard to reason about because it's not in that large regime where it actually corresponds to unbiased reweighting or whatever. This is just reweighting with 4 samples is a little bit I don't know. It's kind of more heuristic at that point.
Okay. So would you are you not happy with the results that you're getting and would say it hasn't been worth it for you to use this?
No, I'm just curious about maybe there are some recommendations on the parameters maybe can be explained in the theory, because if the conditions is null, I need to carefully to select a lambda for every different kind of particle numbers and also even steps. So I choose some different kind of steps. It also influenced the outcome. Sometimes it just converged to the best of n, or sometimes it's being very greedy to just generate 1 or 2 different samples.
Okay.
How often are you resampling?
I used 30, also 100, and then the resample is about 20 steps. But I also used about from 0 to 50%, which is one of the recommendations of the evaluation process. Yeah.
0 to 50%. What do you mean by that? They only sample twice.
No, that sounds to me like the resampling only happens at low noise levels and not.
Yeah.
Oh, sure. Yeah, that makes sense.
But that's interesting. All stuff that's not found in the, or at least not in the first read of the paper.
Yeah.
So have you also tried doing the sampling or the resampling after every denoising step?
Yeah, I have already done something like this as well. And if I do something like this, the 2 converge condition also happens. Sometimes it's just become best of n because the scores are almost the same during every step. So the resample will never be activated because there is an ESS constraint, right? ESS constraint during the sampling process. So every time the ESS is not met, so it will not resample. So it will be just the best of it.
What's this ESS constraint? Do they talk about
ESS, maybe in the appendix. Yeah, it's in the appendix.
Search adaptive use. I'll find the page. Adaptive use. C3. They say that they sample if it's less than half the number of particles, and they skip the resampling step.
Yeah, here, C3.
So high ESS would mean that your weights are pretty uniform, right?
Yeah.
Which is the undesirable thing you're describing, right? You seem to not want them to be uniform because that gives you interest in resampling, or?
This ESS is also influenced by the lambda. So if your lambda is not good, it will never be met. So it will just be the best of n. Yeah, I just report a phenomenon. I think it's maybe interesting, and maybe
Yes.
you have some mathematical points of this problem, and maybe there is a better schedule for the whole hyperparameters. Yeah.
It seems like if your model is very good, then your weights would be roughly uniform. Your ESS would be high, so it would be similar to best of them, kind of, maybe.
Okay, thank you.
Like it's, I'm not that. Don't take that as a firm answer. That's just kind of my reasoning on the. Like it seems like kind of the better your model is, like the closer your actual thing is to the tilted thing. Or no, I guess that wouldn't. Your model would never be the tilted version of itself.
No, I just used the standard diffusion model 2.1 and XL. Oh, I haven't tried XL. No, I just tried 2.1 and 2. Yeah.
Like if your proposal is the actual tilted thing, like if you have some Oracle proposal that's actually sampling the transition kernel of the tilted model, then you would expect to kind of basically be doing best of n, because it's the resampling only really like cuts off trajectories if your transition kernel is giving you things that it kind of shouldn't. But if it's a very good transition, then you expect to kind of like the whole point of like you would have a high ESS already just because it's, and thus you would have this like the idea that things are working well when you're discarding a bunch of trajectories, I think kind of doesn't hold when you have a very good transition already. I actually don't know how related this is to the problem you're describing, so maybe I'll stop there. But
yeah, it's not that bad, because sometimes it doesn't need the resample as well if the whole process goes well. But it is quite interesting because the lambda can influence the whole process. You just adjust the lambda for a little, and the whole transition process will be totally different. Yeah.
I guess the thing that we mentioned at the very beginning, that the lambda, or you're choosing this lambda and you're basically just adding another dimension of model tweakability, comes into or plays a big role here. Okay. Thanks a lot for the insights into some more details of the paper.
Okay, thank you very much.